Okay, chemistry nerdlings, this is an extended little slide on equation manipulation. If there's some of the simpler ones that I've not shown in this set that you need to look at, go over to the Integrated 2 playlist and look at their topic 1, which is equation manipulation, but for some of the simpler equations. We're going to skip right ahead because I kind of expect you guys to have some stronger math skills and look at some of the more complicated ones and the problems that they're doing. So we're going to start off here. This is a statement related to the ideal gas law where we've got velocity root mean square, if you're curious, of the particles. So this is sort of a statistical way to handle all the gas particles moving at different speeds. So kind of related to average. Ideal gas, constant temperature, molar mass of the gas, if you're curious what this stands for. Anyway, we're going to be solving for the molar mass, M. And so the first thing that we need to take care of, doing our order of operations backwards, is we need to take care of exponents. So I am going to square both sides. So I have velocity root mean squared equals 3RT over M. And now I can get at that molar mass now that we've gotten this whole quantity out from underneath the square root. So I can multiply both sides by M. That cancels. And now divide by velocity root mean squared on both sides. And so my final answer is 3RT over VRMS squared. And that's not too bad. Okay, so now we're going to look at a form of Coulomb's law. We've got a constant here, and this epsilon naught is permittivity of free space, and we've got the charges of the two particles and their, radial distance from each other. And this one again is easier than it looks. It's kind of an ugly equation, but if we're solving for this R, it's going to be not any problem at all. I'm going to go ahead and multiply both sides by R squared to get it out of the denominator. And now just divide both sides by force. And take the square root. And there we have that one solved. Okay, so we've got an equation here that you've probably seen in your freshman classes. This is for the total resistance of a parallel circuit, and those are the individual resistors. It's kind of a weird looking beast because we've got total resistance expressed as this inverse total resistance here. So we're going to clean it up and solve it just for plain total resistance. And what I'm going to start by doing is getting a common denominator.
Officer Wade to the front office, please. Sam Wade to the front office.
Get a common denominator here for these two fractions so I can combine them. So I'm going to multiply these both by 1, but I'm going to multiply this one by 1 in the form of R2 over R2. So, not breaking any algebra rules. Multiplying by 1, R2 over R2 is 1. And I'm going to multiply this fraction here by 1 in the form of R1 over R1. R1 over R1 times R2. And now what we have accomplished is these have the same denominator. So we can add them together. And now, if I want this as just REQ, I need to take the inverse of both sides. So I'm just basically going to flip them. And that's a lot cleaner looking than having 1 over REQ. Okay, now we're going to take the same equation and we're going to solve it for R1. So I'm going to do this a little different way just to show you kind of a different way to go about this. It maybe doesn't look quite as pretty as the way that I showed you first, but it's quite all right. So I'm just going to subtract that from both sides. Okay, and now I'm going to take the inverse of both sides again, just to get rid of my reciprocal R1. Okay, and the inverse of this is R1, and the inverse of this is going to be kind of ugly here. But I can write that a little bit neater. By just expressing it as to the negative 1 power. And that's kind of a different way to go about it. Maybe not as pretty, you know, with these negative exponents here, but your calculator will understand it. Okay, this is an equation. This is Bernoulli's equation. We won't actually be using this one in chemistry, but I just picked it for its form. Looks sort of similar to the position function that you might have seen in physics class, but I picked this one because we've got this variable in both locations here. So we're solving for the Greek letter rho, which in this equation stands for the kinetic energy per unit volume of a fluid that's moving down a pipe. So we're going to follow the reverse order of operations, and the first thing that we're going to do is we're going to subtract P1 from both sides. I'm just going to write that in that form instead of having the half rho v squared over 2. And now what makes this really easy to solve is if you notice that the variable that I want is rho, and it's multiplied by both of these terms, and it's to the same power, so I can just factor out rho. And now I can just divide both sides by this quantity right here, and I'll be finished. There we go. And that's going to finish up this chemistry addition to equation manipulation. If there's some of the ones before these on the problem set that you're a little bit stumped with, go over to the integrated science 2 playlist and look at their topic 1. It's also called equation manipulation, just like this one. And you can see me work some of the earlier ones in your problem set. All right.